We're dealing with the phase space for SU2 gauge theory, and our basic variables are harmonics, defined as the path-ordered exponential of the connection integrated on the path gamma, and a flux defined like that. So you take your cotriad, and so you want to integrate it along gamma star, but you have to transport it using harmonics. And I figured out I didn't really write how you write gamma star, h of gamma gamma star explicitly. So you have gamma star here, gamma here with orientations. And so when you evaluate the cotriad at the point gamma star of S, you have to transport it to the point gamma 0. So that reads h gamma gamma star S is, so it depends on whether S is on that side, closer, smaller than 1/2, or on that side where it's greater than 1/2. So let's say if S is smaller than 1/2, you'll have H from S to 1/2, and then that way. So that's H gamma star from S to 1/2, and then H gamma minus 1 from 0 to 1/2, like that. And if S is greater than 1/2, then it means you're on that side, and you have to come back here. So you have to go backwards with respect to the orientation of gamma star. So it's H gamma star minus 1 from 1/2 to S, and H gamma minus 1, like that. All right? So that's the definition. What's interesting is that if I use those formulas with U1 instead of SU2, here it's really what you expect to be the electric flux. Because for U1 it's all abelian, so that guy cancels with that guy. It's really the electric flux for electrodynamics in the U1 case. So it's a natural non-abelian generalization. And the algebra for the Poisson brackets is H gamma, matrix elements AB, H gamma CD equals 0, E gamma I with H gamma AB is H gamma TI AB, and E gamma I, E gamma J, well, it mimics the SU2 bracket, E gamma K. So yesterday I did a sign mistake at the very last line of the calculation for that bracket, because I inverted that, basically. So that's the correct algebra. And so this is the, here, it's the SU2 structure. And here, that bracket, we can actually write it as d by dt of h gamma exponential t ti at t equals 0. So why am I writing it like that? Simply because I want to emphasize the fact that E acts as a derivative on the matrix elements of the harmonics. So it's really that you take exponential t times ti, so it's a translation on the group, and you take the derivative along the direction ti, basically. So it's really a derivative. It's called the left invariant derivative. Left invariant derivative. So why is it left invariant? Because it's a derivative on the right of the group element. So whatever operator I act with on the left, it commutes with this derivative. Commutes with operators acting on the left. Because it acts on the right. So if I have some operators or something that acts as a derivative, usually you expect a finite, the finite transformation that it generates to be some translation, just like the momenta in usual quantum mechanics. So the exponentiated version left invariant derivative would be something like sum over n positive 1 over factorial n. Then I will write alpha I1 I1 gamma. So what this notation means is that I act with the Poisson brackets n times, where alpha is just a parameter to contract the flux, and I sum over n with the 1 over factorial n. So if you look at that, so you just compute the Poisson brackets recursively. That gives you sum over n, and then you have h gamma alpha I n t I n alpha I1 t I1 AB, like that. So it's just h gamma exponential alpha I t I. Okay, it's just to show you how what you know on, let's say, R3 in quantum mechanics generalizes to the SU2 case. Yeah.
What does exponentiated LI mean?
Left invariant derivative. I was a bit lazy to write it. So it's actually right translation. Translation on the right. Okay, and that generalizes to functions. Functions over SU2 in the sense that E gamma I with f of h gamma. So it will be d by dt f of h gamma exponential t ti at t equals 0. and it generates the right translation. G on the function f of h is f of h g. So if you have a function f over SU2, there's an action of the group itself that acts on the right by right multiplication on the argument of f. Okay, and this action is generated by those brackets. Okay, so the situation is that, what we want to do is the quantization. And what we have is a set of variables that Poisson commute. So we can use them as operators that will act by multiplication, because multiplication commutes. And then we have those conjugated momenta that acts as derivative. So the situation is pretty much like the one you know from quantum mechanics. So for the quantization, so you want to represent H gamma and E gamma I as operators. And as operators on a space of function. And need an inner product on that space of function. And it would be nice to find an orthogonal basis for that space. Okay, so we'll do this quantization just for a single edge gamma, single path gamma. So I may drop the notation gamma because everything lives on one path. Okay. So I choose functions psi from SU2 to the complex numbers, and the holonomy H, the matrix elements AB, will act on f of H. So the hat denotes the operator by multiplication. H, AB, f of H. Right? And that actually works for any functions on the group. They can act by multiplication on functions of the group. So I need a notation. Let's say psi of H on f of H equals psi. So I can rewrite that as psi on f being psi f, because these are just multiplications of functions. Okay, in particular, I can write a state f as the function f acting on the constant function 1. One is the constant function. So let us now have a look at the action of the flux. EI on F. Well, so that's EI F on 1. So that's EI F minus F EI on 1. Because E is a derivative. So derivative on the constant function is 0. So that's the commutator EI F on 1. And my quantization map is that commutators equals I h bar times the Poisson bracket. So now I'm going to use this quantization map. So that's I h bar EI with F as operator. That's on 1. So that's I h bar. And then this Poisson bracket, we computed it. That's the left invariant derivative acting on F. So that's d by dt f of h exponential t I at t equals 0 and 1. So I'm just going to denote that by Li on F. So it means the left invariant derivative with along the direction Ti acting on F. That's just a notation because then I want to rewrite that as I h bar Li on F. Yep.
Yeah. So that step when you did EIF acting on state 1, how does it break up into the two parts there? EIF minus FEI. Yeah, just the second equal. Yeah.
Here?
How did you write this? Yeah.
So EI on 1 is 0.
No, I mean,
yeah.
How from EIF on 1, how do you get to that one?
EIF on 1?
Yeah, how do you get to the next step?
So I rewrite EIF on 1 minus FEI on 1, which is 0.
Oh, so it's, okay.
Okay. So maybe I should write here that EI on 1 is 0, identically. Because that's the derivative. So if you apply the formula d by dt here on 1, I mean, where is it? Yeah, the formula above here. D by dt on the constant function, so it's 0. Okay, so basically that's a trick that introduces a commutator, and then you can use your quantization map to rewrite that as the quantization of a Poisson bracket that you know how to compute. Okay, so it seems like we have a representation of our phase space functions on functions over SU2. So basically our state space is the space of functions over SU2, but we would like to equip that with an inner product. That's our second step. So in particular, we'd like the flux to be a Hermitian or self-adjoint operator. And if you exponentiate the flux, you know that you get the right translation over the space of function. And we would like that to be a unitary operator. Yep.
This is a question. So EI is dependent on the group element H?
EI, no, it's a derivative.
Okay, so
F depends on H.
Okay.
F is a function over the group, and this acts as a derivative. So the exponentiated fluxes should act as unitary operators and they generate right translations. So if I have some inner product, it should be an integral over the group. Okay? So I should have F1, F2, being some integral over SU2 with some measure dg, and F1 of, well, let's say H. All right, H. And if the right translation is a unitary operator, it means that it should equal the integral over SU2 dh F1 of hg bar F2 of hg for all g, for any g. Because that should be a unitary operator, so it shouldn't change the inner product. Okay, so it means that we would like this measure dh that I wrote a bit formally here, would like it to be invariant on the right, by right multiplication. So it turns out that for a compact Lie group, you can get better. You can get a measure that is invariant by multiplication on the right and multiplication on the left too. And that's called so it's a measure that is actually unique, and it's called the Haar measure. So that's what we should do now. the unique left and right invariant measure. So it means that dH equals d of hg equals dgh, and it turns out it's also d of h is minus 1. So it has very nice invariant properties. So we can normalize it because the group is compact. Normalization integrals dH of a SU2 is 1. And our inner product is really this formula. And it's indeed such that the left translation and the right translation are both unitary operators. So that equip our space of functions of a SU2 with an inner product. So the state space is L2 of SU2. So it's the space of square integrable functions on SU2 with respect to the Hall measure. So I'm writing SU2 everywhere, but you can change it with any compact Lie group. So maybe we should try to write a bit more explicitly what's the Hall measure on SU2 in terms of some parameters that can be used to put coordinates on SU2. So topologically, SU2 is the three-sphere. It's the three-dimensional sphere as a topological space. So what's more in SU2 than in Ed3 is that you have a group structure. And you can write, so the Hall measure will basically be the natural invariant measure on the three-sphere. Okay. So for G in SU2, you can write G as cosine psi by 2 times the identity plus I sine psi by 2 times some dot product between n and sigma. So this notation here is nx sigma x plus ny sigma y plus nz sigma z, and with psi in 0 to pi, and n is a unit vector. So you know, yesterday I told you that if you have a 2x2 matrix, you can expand it on the basis spanned by the identity and the three Pauli matrices. So that's what we do here. And so you can write n, because it's a unit vector, it's parameterized by two angles, theta and phi. Oh no, what am I doing? So if you have x, y, z, like that, and take a point on the sphere. So that's n. And here you have theta. And then you project it on the xy plane. And there you have phi. Okay, these are the usual spherical coordinates on the sphere. And the H measure reads dg equals 1 over 4 pi squared sine theta by 2 squared d psi sine theta d theta d phi. So basically here you recognize the measure on the two sphere, sine theta, d theta, d phi. And here it's a bit like r squared dr when you are on R3 and you use spherical coordinates. But because it's a sphere, compact space, and not R3, it's somehow compactified and you have sine squared instead of r squared. So if you want, you might think of it as sort of three-dimensional space where the radius is not r, but it's sine of psi by 2. Okay, as I was telling you, that's also the natural measure on the three-dimensional sphere. So it's delta of x1 squared plus x2 squared plus x3 squared plus x4 squared dx1, dx2, dx3, dx4. So you take the natural Cartesian coordinates on R4, and because you want the sphere, you project with delta function like that. So with those coordinates here, for example, you can actually really do calculations on SU2. Because you have a measure defined in terms of coordinates. So here, often we write, when we have a L2 space, we write L2 of the space and the measure.
Excuse me?
Yes, sure.
Doesn't the delta function set the free sphere to have a radius 0?
Sorry?
Doesn't this delta function set the radius of the sphere to be 0?
Oh, yeah, sorry. Thank you. Yep.
Why we want states to be L squared?
That's okay, because the inner product will give you the probability amplitudes, and in particular, the norm of a vector is the probability for that state to So there must be L squared because you want to integrate them on the whole space. And it's just like in quantum mechanics, you have your states are in L2 of R or L2 of R3. Like think of the harmonic oscillator. I mean, this is really, the inner product is what gives you the overlap between states, you know? And a given state overlaps with itself with probability 1. I mean, it overlaps with itself completely. So states are usually normalized vector in that space of functions. All right. So we have our operators, we have an inner product, and it would be nice to have an orthogonal basis on that space. So then we need to do a bit of group theory. So obviously you can write a formal basis. There would be where the resolution of the identity would be integral dg, g, like that. So that would be the identity on L2 of G of SU2. So it's exactly like you write integral dx xx in quantum mechanics. And basically, f of g is g f. And the brackets between two group elements should be delta of gh minus 1, where delta is the Dirac delta. Such that integral dg delta of g minus 1 f of g equals f of h. So the notation means that what's inside the delta should be the identity. So g h to the minus 1 should be 1, which means g equals h. And that's the definition of the delta function. Okay, but this basis is labeled by a continuous variable, which is a group element. So we'd like to have something a bit less formal with which we can actually do calculations. So typically, if you were to work on U1, you would use a Fourier transform. Instead of using angles on U1, you would use the Fourier modes and use the Fourier expansion to expand any functions over U1 by its Fourier expansion. So here we're going to do the same on SU2, all right? Okay. So we need some representation theory. So what's a representation? It's, well, you have a group of symmetry and a system, a physical system, and you'd like the symmetry to act on your system as operators or transformation. So it's what we call a representation. And basically, a representation rho is a map from your group G onto GL, the general linear group on V, where V is a Hilbert space. So rho is a representation of G onto the Hilbert space V, which means that for each group element, you get a linear transformation that acts on V, on your Hilbert space. So to each group element G, you get rho of G as an operator on V. A unitary representation is a representation such that rho of G is unitary for all G. Okay, that would be a map from G to the unitary group on V. So obviously, if I give you a group and you try to find all the representations, there are infinitely many, so it's a mess. So you'd like to classify them. And for example, if I give you two representations in spaces that look different, you might want to find whether they may actually be equivalent representations. You know, even if the spaces look different, they may be isomorphic, and the two representations may be the same. So you need a notion to find equivalence classes of representations. So two representations are unitarily equivalent if there is a unitary operator U such that rho 1 equals U, rho 2, U minus 1. Or equivalently, rho 1, U equals U, rho 2. So that's also, U is what we also call the intertwiner, because it intertwines the actions of rho 1 with rho 2. You know, you can act first with your representation rho 2 and then with the unitary operator, or first with the unitary operator and then with rho 1. Now, when you act with, let's say, the rotation group SU2 on a physical system, your physical system may have different blocks where the rotation group will act sort of independently on these different blocks of your physical system. So there's notion to say whether your representation is actually reducible or not, whether you can find subsystems in it. So it's called irreducibility or reducibility. So a representation is reducible if there is a subspace subspace V prime in V that is non-trivial. And such that V prime is left invariant by rho. So it means that rho of G acting on any vector V prime is contained in V prime. So we'll be mainly interested in irreducible representations, which are representations such that you cannot find a subspace that is stable under the action of the group. So now let us have, I will just give you the representations for SU2, so the irreducible representations. So we call them irreps as a short name. So I'm going to tell you about irreducible representations up to unitary transformations. So these are rather equivalence classes of irreps. So they are labeled labeled by a spin. Which is the dimension of V. So a spin that we denote J, which is the dimension of Vj in 2j plus 1, where J is a half integer. So if you give me some irreducible representation of SU2, up to a unitary transformation is something that will act on a vector space of dimension 2j plus 1, where j is some half integer. And we call j the spin. So I can tell you about the first three examples, where j equals 0, 1/2, and 1. So j equals 0, that's the trivial representation. Trivial irrep. Because rho of g is just the identity for all g. And it's a one-dimensional representation. One-dimensional irrep. So it acts on C, set of complex numbers, and all group elements are mapped to the trivial, to the identity operator. So it's really the trivial representation. You don't see rotations there. So if you want a non-trivial one, you have to go to non-zero spin.
How can a trivial how can a trivial representation be irreducible?
Well, I checked the definition. Is there a subspace?
If it always acts as an identity,
Yeah.
then couldn't there be a subspace that is left invariant by the identity?
right, so it's a sort of degenerate example. Right. But we need to include it, actually. Well, okay, the definition means really a non-trivial subset that is different from 0, but different from the full space, because obviously the full space is left invariant. So in that sense, it's really a irreducible representation. Yep.
Why do you say it's one-dimensional?
I'm just telling you it's a one-dimensional representation. If you apply that formula, so the dimension of the representation space is 2j plus 1, so j equals 0. That's one-dimensional. And actually, if you want to represent rotations on a one-dimensional space, the only solution is the identity for each group element. Yeah, so in the definition of reducible here, it's a subspace that is contained in V and, well, different from V. Okay, so next example is J equals 1/2. So the dimension of V J equals 1/2 is 2. So do you know a two-dimensional representation of SU2? I guess you do, because that's just SU2 as 2x2 matrices. So it's called the fundamental represent You know, I defined SU2 as a group of 2x2 matrices satisfying some properties, and it acts on C2 naturally because these are 2x2 matrices. SU2 as 2x2 matrices. Okay, so it's a simple one. Then J equals 1, and then I stop. So Gym of V for J equals 1 is 3. So it's called the vector representation, Urep, and it's actually SO3. So rotations on vectors, on 3 vectors. Okay, so these are the natural examples. Okay, so then we have the Peter-Weil theorem that I'm not going to prove. And it states, so pick up a complete set of equivalence classes of E-reps. So here for us, that's the representation rho j. Rho j being a half integer. So each representation acts on a finite dimensional space of dimension 2j plus 1. So we can find an orthogonal basis in each Vj. Okay? So pick up an orthogonal basis on Vj. And write the matrix elements of the representation as D, J, G, M, N. Okay, so I take a basis on each Vj, and then instead of rho, I'm now using the letter D because it's the canonical choice for SU2 if you read books. So it's dj of G of a group element, and that's a matrix acting on Vj. So it has matrix elements dj of G, Mn. And M and N both go from minus J plus 1, and so on, up to J plus 1 to J minus 1, J. Because it's 2J plus 1 dimension. Okay. So all these notations are the standard ones you can find in books, so I'm not creating them for fancy reasons. And dj of G, they're called Wigner matrices. In the SU2 case, they're called Wigner matrices. So you can note that in the U1 case, the representations are labeled by an integer that may be positive or negative, and the matrix elements are just exponential I and theta. So it's really the Fourier modes. So I didn't state the theorem so far. I haven't stated it. I just told you pick up a complete set of irreps, an orthogonal basis on each representations, and then the theorem states that you have an orthogonal basis. Where am I? Then the set of all matrix elements in all representations is an orthogonal basis. Of L2 of SU2 with the Hall measure. So that's the theorem, basically. Okay, so just to conclude that, I'll write two equations. That actually translates this theorem. So the orthogonality reads integral dj of g m j prime m prime n prime complex conjugated dj of g m n equals 1 over 2j plus 1 delta j prime delta of m prime delta of n prime. So everything's orthogonal here. And completeness, because that's the basis. Completeness. So denote those matrix elements as G on J, M, N. And you have sum over J, all half integers, sum over M and N from minus J to J of J, M, N, J, M, N. That's the identity on L2 of SU2. And it means that any function f of g over SU2 has an expansion like that. M, N from minus J to J, F, J, M, N, E, J, of G, M, N. So it's really a generalization of the Fourier transform. That's the final equation for today. So if you apply that to U1, you get the Fourier transform. And obviously, so those guys are the Fourier coefficients. Fourier coefficients. And you can get them by integrating your function against a Wigner matrix. Basically, you take the inner product between f and one of the matrix element of a Wigner matrix. Okay.